So we'll continue our discussion from yesterday. So we have introduced this electronic circuit component called rectifier. A rectifier, as we discussed, it is a electronic circuit component that can convert AC signal into DC signal. And also in our discussion, we have already talked about AC signal, alternating current signal. As we see it, within one cycle of this alternating current signal here, you have positive half of the cycle and negative half of the cycle. And the positive half of the cycle is between the phase angle of 0 and pi. Negative half is between pi to 2 pi. So the subsequent cycles are just a repetition of the same cycle, and the number of cycles per unit time gives you the frequency of your AC signal. And we also said that during this positive half of the cycle, the current direction is in clockwise, and during the negative half of the cycle, the current direction is reverse anti-clockwise. Okay, so within one cycle also, within a very, very small fraction of second, current direction will be reverse. However, in the DC signal, in the DC current, you have a unidirectional flow of current, right? And here, when we design a half-wave rectifier, we have said that we need a transformer in order to step down from the high voltage that is supplied to our household electrical power, our electrical signal. And there we can using this transformer, we can step down to 230 volt to whatever desired value, depending on the number of turns in the secondary and number of turns in the primary, that is the transformer ratio. And in India, our household power supply, there is it has a 50 hertz AC. That means there will be 50 cycles per 1 second. And yeah, so also we discussed that diode behaves like a rectifying device in the sense that in the forward biasing, diode has a very low resistance. The forward biasing diode has a very low resistance. However, when you do a reverse biasing from the IV characteristics, we calculated the resistance and all. Here, even for a very large change of voltage, hardly there will be any change in current in the reverse biasing. That means this ratio del V upon del I, that will be very large. So in reverse biasing, the current that can flow through this diode is in microampere, that is very, very small. And therefore, we can say that no current can pass through diode, no current which can be detectable, or sufficiently large current which can be detected by normal ammeter, and also which can be detected by which can be utilized for our devices, right? So like in our laptop or in our mobile phone charging and all these things, the current that is passing through our devices is in milliampere. So milliampere is certain current which can be utilized, right? Which is sufficient for most of our electronic devices. Milliampere currents are. So therefore, only in the forward biasing you have milliampere currents. In the reverse biasing, 10 to the power minus 6 ampere means that is too small and it cannot turn on your devices. It cannot give any glow to your LED light also, right? So therefore, we can safely say that diodes permit flow of current only in one direction, right? Now, moving on to that device, that rectifier device. Now, here, if you look at this circuit diagram, the one I drew here, we are using one diode here in this half-wave rectifier, and we know that the secondary of this transformer also will have the true half of the AC signal, that is the positive half and the negative half, that is between 0 to pi and pi to 2 pi. And as you can see, during this positive half of the cycle, the upper side of the secondary coil of the transformer will be positive and the lower side will be negative. Now, if you look at this polarity of the AC signal here during this positive half of the cycle, you will find that positive signal is connected to P type. So I have already explained that this is a diode symbol. So if you have a PN junction diode like this, P type, N type, and the corresponding symbol is like this. All right. So this side of the symbol is indicating a P type of the PN junction. The other side will be N type of the PN junction. So you have a PN junction diode like this. And if you connect positive terminal to the P type and negative terminal via the load resistance to the N type like this, it will forward bias your PN junction device. Okay, so if it forward bias the PN junction device, like I explained there in the IV characteristic curve, under forward bias, this PN junction will allow flow of current, Therefore, as you can see, this side is positive and the lower side is negative, means current will flow from top to bottom across this load resistance during the positive of the cycle. Now, when you have this negative half of the cycle connected to this secondary of this transformer, there will be a phase reversal. There will be a reversal of the signal. That is, the lower side will become positive, the upper side will become negative, and the upper side of this secondary coil of the transformer will be negative. Now, under this cycle, that is pi to 2 pi, negative signal will be connected to the P type and positive signal will be connected to the N type via this load resistance. Therefore, under this cycle between pi to 2 pi, you will have PN junction reverse bias. So if the PN junction is reverse bias, like we explained in the IV characteristic curve, no current can pass through the PN junction. The current passing to the PN junction is only in microampere. Those very small currents are due to the reverse saturation current, like we explained yesterday. Now, then we can say that no current is passing through this PN junction under reverse bias. All right. So now let us write down that whatever we discuss in mathematical form. Now, here is our input signal. This is, let's say, our input signal. Our input signal means the signal we receive from the secondary coil of the transformer. So the secondary coil of the transformer will give you a signal something like this. All right. So this is one cycle, and this is the next cycle. And now, what will be the voltage across the load resistance? The voltage that will appear across the load resistance, let's say V0, will be the current passing through the load resistance into resistance value RL. So I into RL, here we have written that RL is the resistance, RL is the resistance in this load circuit. And let's say I is the current passing through this circuit. Okay. Now I into RL will give you your voltage. Now, as I have just explained, during this positive of the cycle, current can pass through it. Current can pass through it means current into resistance multiplication will be finite. So depending on the resistance value and the current value, you will have a certain amount of load resistance. However, during negative cycle, so the current is zero. Current is zero means output voltage in this cycle is zero. And during this next positive of the cycle, you will have a current passing through the load resistance and correspondingly multiply with the resistance. Then you will get the output voltage like this. And current will be zero. Okay. So in this circuit, as you see, by the introduction of this diode, it allows the current to pass through the load resistance only in one direction, that is from top to bottom. Current flowing from lower, like bottom to top, that is anti-clockwise direction, is now suppressed. So when you are connecting the voltage in a reverse cycle like this, the diode is reverse biased. That means the current that is supposed to flow in the anti-clockwise direction is now suppressed. Right. So only one half of the cycle will be uh, passed on to the load resistance, and you will have a current flowing to the load resistance only in one direction. That kind of unidirectional flow of current is what we call it as a alternate direct current, DC current, DC signal. Now, so this is how we represent the input signal. Vm is the peak value of the AC signal, like I discussed before. And here what is the total resistance of the circuit? Total resistance of a circuit here will be, you have your load resistance, and under forward bias we have said that there is a small forward resistance RF. Yesterday we talked about this RF, small forward resistance. So the equivalent resistance of this circuit is okay. The equivalent resistance of this circuit will be, now you see that this circuit, diode circuit, and the load resistance, they are connected in series. So if they are connected in series, then it will be forward resistance plus load resistance RL. So you have your equivalent resistance as RF plus RL because they are connected in series. Therefore, your total resistance of the circuit is RF plus RL, equivalent resistance. Then the current that is passing through the load resistance will be your voltage divided by resistance. According to Ohm's law, the voltage is equal to resistance. So the current passing through the load resistance will be voltage upon resistance, equivalent resistance. Okay. Now, so current will pass through the load resistance only within this cycle, that is 0 to pi. So within this 0 to pi, you have this much amount of current. But within pi to 2 pi cycle, the current will be 0. Okay, within pi to 2 pi, the current will be 0. Now, defining peak current as Vm, peak voltage upon total resistance. So you can just rewrite your current as this. Okay. Now, here in this rectifier, we will come across a certain term like DC current, AC current, root mean square current, and all. So DC current is the average current during one complete cycle. The average current during one complete cycle of an AC. So one complete cycle is between 0 to 2 pi. Then to take the average, you have to sum up the current value during that complete cycle. In order to sum the current value during that complete cycle, you have to integrate from 0 to 2 pi the current value. Then divide with the interval. What is the interval? The interval will be 2 pi only. That you can obtain it by integrating from 0 to 2 pi, just like this. So the interval, this integration will give you 2 pi only. All right. So taking average means you are summing up the value of the current during one complete cycle and divided by the interval of that cycle. So 0 to 2 pi, you can split into two parts, that is 0 to pi positive half and pi to 2 pi negative half. During this positive half, the current value is this, and during negative half, as we have just discussed, the diodes will suppress the negative cycle of the signal. The diode will not permit the current to pass through it. That means it will suppress the negative half of the cycle. Therefore, this will be 0. And here you can do the integration here. Integration of sine omega t with respect to omega t will be minus of cosine omega t, and then you can do the mathematical steps. So you put the upper limit and lower limit. Cos pi is yeah, if you take minus im as a common factor here, cos pi will be minus 1, minus of cos 0 will be 1. So like this, 2 and 2 will cancel out. This will be your DC current. Okay, this is the average current that flows through the load resistance of your rectifier circuit. Now, there is this another current, which probably a new term for some of you. We call it root mean square current. Root mean square current means it is the equivalent of an DC equivalent of an AC current. See, an AC current, it is an alternating signal. If you put a voltmeter, since the current direction is the current direction gets reversed within a very small fraction of second, your normal voltmeter will not be able to read such voltage. It will not be able to give you such voltage because it will be like within a very small fraction of a second. So you cannot really notice or get a reading out of your voltmeter. So in order to measure an alternating current signal, uh, we use an AC ammeter. So what an AC ammeter measures is the root mean square current. So an AC ammeter can record the root mean square current of that AC current. Okay, so uh, so RMS value of an AC current, it is the DC current, right, which produces the same amount of heat energy as that of AC current. Suppose you pass through an AC current in a certain heating coil, and also you pass through a DC current in a certain identical coil. If the same amount of heat is generated by the DC signal as that of your AC signal, then the value of the DC signal is what we call a RMS current. Okay, RMS current. So as the name implies, root mean square current means you just take the root and you just take the mean and you take the square of current. So you are summing up the square of current in this interval 0 to 2 pi divided by the interval that is 2 pi here. That will give you an average. Then you take the root mean square current, right? So then this integration, that is the interval that is between these two, this is 0 to 2 pi only, so the interval which is 2 pi. So when you integrate this, you will get 2 pi again, and you get the square root of 1 upon square root of 2 pi. And if you integrate this, your I value, you know, I m square, sine square, and all these things, and during this cycle pi or 2 pi again, it is 0. So you can take out I m as a common factor, and also you can write sine theta, sine square theta as what is that? Sine square theta will be 1 minus of cos 2 theta upon 2, right? 1 minus of cos 2 theta upon 2. So if you follow the trigonometric formula and then perform the integration, so this is what you will get, Im upon 2. So your IRMS, the root mean square current, is peak value of the current divided by 2. Peak value of the current divided by 2 will be your root mean square current in this half-wave rectifier. Okay. Now there is this thing called efficiency of a half-wave rectifier. So efficiency, when we talk about efficiency, it is a measure of the performance of that device. So our device here is a rectifier, means our device purpose is to convert AC signal into DC signal. So how efficiently your rectifier can convert AC signal into DC signal is known as your efficiency of the half-wave rectifier. So it is just the ratio of the DC power appearing across your load resistance upon AC power in the circuit. AC power in the circuit, AC power connected to the circuit. DC power appearing across your load resistance to AC power connected to the circuit. So you are giving certain amount of AC power to this half-wave rectifier, and you are measuring how much amount of DC power is there across the load resistance as the output power. All right. So then only you will know how efficiently your rectifier can convert AC into DC. So this efficiency, the symbol is eta here, Greek letter. So DC power upon AC power. DC power across the load resistance means the power is P equal to IV, right? So your DC power means DC current, I DC in, so your power means P is V into I. V is I into R. So it will be I square R. Power of an electrical signal is I square R. Right. So you can just put the value of current, your DC current, to get the DC power, IDC square into RL. And you can also get the AC power connected to the circuit. So as I said, you have this thing, secondary coil, and this diode, and this load resistance RL. So you are giving AC power via this transformer. So how much AC power is circulated or given to this circuit means you have a feedback resistance, you have a load resistance. So it will be root mean square current into RF plus RL. Okay, so then you do the simplification, you take the ratio of this, and after the simplification, cancel Im square and all, this is what you will get. Usually the load resistance RL is quite high, much greater than your forward resistance of a diode, because forward resistance of a diode is, if you look at the IV characteristic curve, the diode is flow following like this. That means the forward resistance is very, very small. Okay, so that means this is negligible in comparison to this ratio. So this ratio can go is approximately 0. So this will be as good as 1. So if you do that, you do the mathematical like this division of 4 with respect to 3.14 and 3.14, then you multiply it with 100% converting to percentage, you will get the percentage efficiency as 40.6. Okay. Now, there is this thing called, this term called ripple factor. So, you know that, like, if you connect a battery like this, if you connect a DC battery like this, and let's say you have a certain load resistance RL, so you have a voltage, so you can have a DC current passing through this. The DC current passing through this will be I is equal to V upon RL. It will have fixed value. This DC current will have fixed value because the voltage is fixed, means the current passing through the resistance is also fixed. So if you plot it like this, this is, let's say, zero current. Let's say this is your current. The current value, if the current passing through this is 5 ampere, it will remain 5 ampere throughout, if you pass current, if you connect the circuit for, let's say, 10 minutes, let's say 20 minutes, current passing through the resistance will remain fixed and flat line like this, 5 ampere. But if you remember, the output of a rectifier is like this: one half, second half is suppressed, and positive half current is passed through in the passed through the circuit in the positive half, and the negative half is suppressed again. So this is the unidirectional current. Unidirectional current or unidirectional signal you can obtain out of your rectifier. Now you see that the output of this rectifier, even though it's a unidirectional flow, it is not identical with your usual DC current here. Your usual DC current coming out from this battery is fixed, constant, flat line. However, in this rectifier output, you have a DC current increasing and decreasing to 0, suppressed, remains 0 for some time, increasing and decreasing to 0 again. So that means it is not entirely identical with your DC signal, nor from the battery. Therefore, it shows that there is still certain AC component. There is still certain AC component in the DC output of a rectifier. There is still certain AC component in the DC output of a rectifier. That AC component in the output of a rectifier is known as ripple. Okay, is known as ripple, or you can say that ripple is a measure of the amount of ripple factor is a measure of the amount of AC component that are present in the output of the rectifier. Okay, ripple factor is a measure of the amount of AC component that are present in the output of a rectifier. So simply it is defined as a ratio of AC current to DC current. So as I said, this output has AC as well as DC. So the RMS current so is related to the pure AC and the pure DC like this. I square RMS equal to I square AC plus I square DC, the pure AC component and pure DC component. So the pure AC signal will be written like this if you rearrange it. Then the ripple factor, this is R, small letter R. Okay, the ripple factor will be IAC, that is this quantity upon IDC. Now, if you do certain simplification, so you will arrive at this. So actually, there is a mistake here. Yeah, okay, that square should not be there. So I RMS upon IDC whole square minus 1. So if you put the value of IRMS, we calculated, put the value of IDC, we calculated, then you will get the ripple factor as 1.21. That means there is a large component, there is a significantly large amount of alternating current signal component. Significantly large amount of alternating current signal component in the output of a rectifier, half-wave rectifier. Okay, so up to this point I want to conclude my lecture for now. So we can have another like C++ programming class at 1:15. So I'll stop now. I'll take 15 minutes break and then we can continue. Okay, if you have typed your attendance, you can exit the meeting. Or if you have any question also, you can ask. And another announcement is that you can actually, what is that? You can actually collect your answer book, mark book, grade sheet from the college. If it's convenient for you, you can visit the college. They are giving out the mark sheet. So you can collect your mark sheet from the college office during office hour. Okay.